All right, so homework number 9 deals with the issues of dimension of the vector space, looking at the kernel of a linear transformation, and we already showed that that's a subspace, and now we just want to find the basis for that subspace. And we want to define coordinate vectors and how to find them relative to the basis, and then how to find transition matrices which take coordinate vectors relative to one basis and give you the coordinate vector relative to different bases. Okay. So we saw that the basis for a vector space is not unique. So we don't talk about the basis for a vector space, but rather a basis. So there could be many different bases for the same vector space. So for example, if you take the vector space R3, we said that, well, here's a basis. Let's call it as or standard basis. And these are linearly independent and they span R3. And here's a non-standard basis. This set is also a basis. If you stick these column vectors into a matrix and find the determinant, it'll be non-zero. But you have infinitely many bases for R3. But what can we say is, what's invariant though? The number of basis elements in a basis for a vector space is invariant regardless of what basis you use. So that's always, the number of basis elements is always the same, even though the basis elements can be different. So for example, R3, every basis consists of 3 elements, right? So we can talk about, so this invariant defines what we call the dimension of the vector space. So given the vector space, the dimension of it is the number of basis elements a basis must contain. It's always the same, right? It's invariant. So if you take Rn, the dimension is n. These are just some examples, right? We have n entries. You can always think of a basis consisting of elementary columns. Let's see, the dimension of the set of polynomials degree n or less. What's the dimension of that space? N plus 1. Right. So if you look at Pn, this would be the set of all polynomials degree n or less. So every one of these things looks like this, and the a's are real numbers. So here we have, just by itself, here we have a1 through an. That's n parameters that define some polynomial. But then you have this constant, this extra one. So the dimension is actually n plus 1. So that's it's good to clarify that, right? Because the dimension of Rn is n, but the dimension of Pn is n plus 1 because of this constant. Think of this as the 0th degree extra. All right, what about the dimension of the set of n by n matrices? What would the dimension be? N times n, right? You think of like each entry as being an independent parameter, so you have n by n entry, so n times n. So these are all examples of vector spaces that have finite dimension. Are there vector spaces which have infinite dimension?
Yes.
Sure. So, I mean, I can think of, let's say, the set of functions, or maybe the set of polynomials. Yeah, let's do the set of functions as a vector space. You add two functions, you get a function. Let's say on the real numbers. I think your book would denote this with f for functions, and then undefined on the real numbers. That's a vector space. You can scale a function and still get a function. Well, how would we, and it's infinitely dimensional. The dimension of the space is not finite. I'm not even saying what infinity really is or isn't. I'm just saying that the dimension is not finite. So how do we go about proving something like this? Well, what you can do is you can show that if you have a subspace in this vector space, right, a vector space in its own right, and you can show that you can always find a subspace larger than the one you just gave me, then, well, let's just do the example. Okay, so imagine the subspace as not, it's the span of the number 1. Okay. So this is the set of all constant functions. If you scale this by any amount, that just defines a function on the number line where it's always the constant function. What's the dimension of that? What's the dimension? No, the dimension is 1. Because this is a basis element for that subspace, right? Any scaled version of this function is in our set. So this is a basis. And the span of this number is just all multiples of that number. The dimension is 1. S1, let's say, defined to be the span. And x. So this is the set of all functions which we call, we say the graphs are lines. I shouldn't call them linear functions, but so it's all multiples, all linear combinations of these two functions. So what's the dimension of that space? 2. There's two basis elements, 1 and x. These are independent. Right? You can't write x as a multiple of 1. We're using this to scale a number. And so you can see how this just keeps growing. If I consider the span of 1x and x squared, now I'm talking about the set of all polynomial quadratics, right? Polynomials of degree 2 or less. And so on. That's p dimension. So now imagine that we have S sub n. So that would be the span of 1, x squared, all the way through xn. That's n plus 1 dimensional. And can I ask you, is x to the power n plus 1? That's a function, right? Yeah.
So is the dimension of S2 3?
Yes. Right, we have 3 linearly independent functions which span the set. So this is a function. Is it possible to express this function as a linear combination of these? It's not possible, right? This is not a like term. This is like x to the power 7. This would be x to the power 6. It's not possible. So this function is not in the span of those. Okay. So I can add this function into this set, and I get something which is one-dimensional height, right? So that'd be Sn plus 1. Because I'm adding a new vector function, which is not a linear combination of the preceding one, so we've raised the dimension by 1 by adding that new linearly independent, independent vector. Okay, so this is a kind of inductive proof. I'm mentioning this obviously because of the first problem in your homework. It's kind of similar. So if you have, so you can inductively we see that give me a number, right? We have a subspace of that dimension, but we can always find a subspace one dimension larger. Okay, so that proves that there is, right? So if you have that these guys are a subset of these functions on the real numbers, but there is no largest dimension, that means that this set must have infinite dimension, right? Because you can always find a subset of whatever dimension you want, subspace of whatever dimension you want. So there's no upper bound on the dimension of S sub n, right? Because you can choose n to be arbitrarily large. Okay. So that proves that this is infinite dimensional. Okay, so the second issue, thing we're going to discuss is a kernel of a linear transformation. We mentioned this at the end last time, I believe, where we said that we did it in terms of matrices. We had an equation, matrix equation, A times x equals 0, and we said that the set of solutions to that equation, and we proved it, is a subspace of some Rn. We proved that if we have a subspace, i.e. a vector space, right, we hope to find a basis for it, a basis. So let's practice that. So for example, suppose we have a transformation which takes a vector in R3 and gives you a vector in R3 according to this rule. Oh, and by the way, kernel of a linear transformation, right? So the kernel of a linear transformation is exactly the set of solutions to this equation. It's all the vectors in the domain here, such that when you stick them into your transformation, you get the 0 vector in the code. So you see how it's analogous. So kernel is the set of solutions to this homogeneous equation. It's a subspace. And we hope to find the basis for that. So how would we do that? Well, what's the matrix representation of this? I mean, this almost defines itself, right? We have the matrix of coefficients for x, y, and z respectively in that order. That's that matrix. So the set of solutions to this equation is the set of solutions to the matrix equation. Right, we want to know which vectors, x, y, z, multiply this vector in the domain, give you the 0 vector in the code relative to the kernel. Well, of course, we solve this system by, say, row reducing. This matrix happens not to be invertible. And again, a little unnecessary, but I'll go ahead and augment the matrix with coefficients on the right-hand side and start row reducing. And I won't even write down the row operations, but wow, okay. I'll go right to that. Into more row operations. Gives the, I think, the reduced echelon form of the matrix. Okay. So now we read off the solutions to the equation. And again, that's just shorthand for system of equations. So the bottom row just says 0 equals 0, no information. The top row says that x minus 16z must be 0. The second row says that y minus 19z must be 0. So clearly we're going to let z be any number. We have infinite many solutions where t is a real number. And then we can easily define x in terms of the parameter t. So we say that the kernel of this transformation then is going to be the set consisting of x, y, and z, where x is 16t, y is 19t, and z is t. And notice that I can think of this as like factor out the t. This set of solutions to this homogeneous equation can be thought of as all multiples of the single vector. Right? It's the span of that vector. So this subspace can be expressed as as a set of all multiples of this vector. So this vector spans the set, and it's a single vector. So it's linearly independent automatically, right? Except the only time a set containing a single vector is not linearly independent is when that vector happens to be a single vector. So this is a good basis. The single vector is a good basis. And what's the dimension for the kernel in this case? 3. So the set containing this vector is a basis for the kernel. We see that our basis consists of exactly one element, so the dimension of the kernel here is 1. Okay, end example. So, the problem in your homework is a little bit more abstract, but let's see. So, in your homework, it would be something like U is a let's do an example. So U is a 5 by 1 matrix, so i.e. a column vector, right? And then you consider the transformation the vector x defined by U transpose times x. And that's a linear transformation because it's just a matrix multiplication. What dimension would the domain be of this function? Well, where is the x from? What space? Okay, so U transpose becomes a row vector. What kind of vector would that have to multiply for this to be defined? A vector with 5 entries, right? So x is from R5. That's the domain of our function. And it's a matrix multiplication, so it's a linear transformation. And so we want to think about the kernel of this linear transformation. That's just a set of all solutions, all the vectors in the domain, such that in the transformation it returns 0 for that vector. Definition of kernel. Well, how would we solve this? Well, if we set this transformation equal to the 0, it's a 1-by-1 matrix, a number. We would be looking for solutions that look like to this equation. So 0 times x1 plus x2 minus 2x3 plus 3x4 plus 0 x5 is 0. And we should kind of recognize this is an equation of a plane in higher dimensions, right? This is a hyperplane. So what is a hyperplane in R2? It's a line through the origin. So you can imagine that you have like x and y, and you have y minus some multiple of x, right? I mean, it's x1, x2. That defines a line through the origin, and that's a hyperplane. It's a one-dimensional subspace of R2. Well, what's a hyperplane in R3? Well, it's a plane, right? That looks like. And so on, in general. So this is just a generalization to higher dimensional, a generalization of a plane to higher dimensions. And what would the dimension of this be? In this example? Well, what's the set of all solutions to this equation? What restrictions do we have on x1 according to this equation? None at all. Right? X1 can be anything. Like this doesn't because x1 is being multiplied by 0. X1 can be anything. So we would say let x1 be a parameter R. Let's see, do we have restrictions on, well, let's just do x3. So think of it, okay, so if we solve for x2, right, we can let x3 and x4 be anything. That's in T. But then x2 is completely defined by this equation. It's completely determined. It's 2s minus 3t. And then we have x5, which could be anything, so rstu, let's call it u. Let x5 be u. So r, s, t, and u are any real numbers. Okay. So the set of vectors of this structure is the kernel of our transformation. And what's the dimension? Well, can we find the basis? Yeah, it's 4. We have 4 parameters. Can we find the basis? I think so, right? So this vector can be expressed as, let me just do it quickly. That's an S out of 5. Okay, so think of this as a vector containing just the R's. So you're probably familiar with this procedure right now. Just the S's. Just the T's. And just the U. So you should agree that if you add these up, you will get this original. bring out V. Parameters. Okay, so it looks like anything that's in the kernel or transformation can be expressed as a linear combination of these four vectors. So those four vectors will span that kernel. And because you got these column vectors from a reduced, well, okay. And then you can also show that they're linearly dependent. Yeah, if you take a matrix and you reduce row echelon form the thing, the columns you're going to, things you're going to get are going to be linearly dependent. Not the columns, but basis. You're going to get a basis. This is you can show that this is linearly dependent. So these four vectors create a basis for the kernel. Therefore, the dimension of our kernel is 4. Notice the dimension is 1 less than R5, right? So the dimension of any hyperplane is always 1 less than the dimension of the plane. Just like a line is one-dimensional subspace of two-dimensional R2. A regular old plane is a two-dimensional object living in three-dimensional R3 and so on. Okay. Your homework is just a little bit more abstract. You have arbitrary dimension. So, just move on. Right, so now we want to define a coordinate vector. Last time we defined coordinates. So let's see. So suppose you have a vector space. Let's just, for sake of argument, say it's three-dimensional, and this is a basis for that space. Right. I'm just dealing with three dimensions for clarity's sake. And suppose that this is another basis. For the same space. These are two bases. Bases for, say, three-dimensional vector space. So what are the coordinates? So if you take, the notation here is logically clear, but it's as easy as learning to juggle, to get used to it. But V is a vector. Maybe I shouldn't use V. Yeah, I should. It's a vector in the vector in V. So this vector can be expressed as a linear combination of the basis elements A, right? Because by definition, every vector in this space can be expressed as a linear combination of the basis elements. So we know that this vector can be expressed as a linear combination of the u's. And the coefficients in that linear combination are called the coordinates. Coordinates of the vector V relative to the basis A. At the same time, the same vector V can be expressed as a linear combination of the elements of the other bases, right? So it can be expressed as beta 1, V1, beta 2, beta 3, V3. So the betas here are the coordinates of the same vector V, but relative to a basis V. So it's this. This is the same vector. Just we have two different coordinate representations because we're using different bases. So the question is, okay, so now let's define coordinate vector. So a coordinate vector would be relative to a basis, say A. Right? That would be exactly, the notation is like this. Here's the vector, and the coordinate vector relative to basis A is exactly that column vector whose entries are the coordinates. So alpha 1, alpha 2, and alpha 3. So the coordinate vector consists of the coefficients in the linear combination of the basis elements that give you the vector B. So we would say you take the same vector, and now the coordinate vector relative to basis B would be the column vector whose entries are the coordinates relative to basis B. Beta 1, beta 2, beta 3. So notice that I could have the same vector, but it has two, but the coordinate vectors are different because you're using different bases. All right. The question is, how do you take the coordinate vector of a vector, right, and transform it into the coordinate vector for the same vector but with respect to different bases? Let's call it the transition matrix. And we may justify it this way. So let's define transition matrix. Transition matrices multiply coordinate vectors relative to one basis and return the coordinate vector relative to a different basis. So we write P, I don't know why they use P. I wish I should have looked that up. But suppose so the transition matrix P is going to, from A to B, it takes the coordinate vector with respect to basis A and returns the coordinate vector with respect to basis B. Its job is to multiply coordinate vector with respect to basis A and return the coordinate vector with respect to basis B. And the transition matrix from B to A multiplies coordinate vectors with respect to basis B and returns coordinate vector with respect to basis A. Now, both of these coordinates vectors are representing the same vector, just a different coordinate representations of it. So how would we set this up?
Over here.
So we're going to take advantage of the fact that this is exactly the same vector. So these things are equal, right? These things are equal. Because B is the same vector. We're going to write it as a combination of the basis elements in A. And that should be the same as a linear combination of the basis elements in B. So now we can, let's recall that interpretation of, suppose these are column vectors. So let's recall the interpretation of matrix vector multiplication where the linear combination of these column vectors, say, is exactly the matrix multiplication of the matrix consisting of the columns, U1 through U3, times the vector whose entries are these coefficients. So that's the left-hand side. And on the right side, again, I'm sticking these vectors V1, V2, V3 into columns of the matrix. And then the entries. So now, just for convenience, call this matrix A. And this is, of course, what? The coordinate vector of B. relative to basis A. Right? That's just the entries are the scalars in our linear combination. And let's call this matrix B, because the columns are the basis elements, B. And that's multiplying the coordinate vector of V with respect to basis B. So now if I want a transition matrix from A to B, what kind of algebra can I do to get that? Remember that this transition matrix multiplies coordinate vectors with respect to basis A and will return coordinate vector with respect to basis B. Well, I just multiply both sides by the inverse of B. And these columns being vectors in a basis will have a determinant that's non-zero. The determinants are guaranteed not to be zero. Therefore, these matrices are invertible. So this will be exactly B inverse times A. And if we want, on the other hand, the transition matrix from basis B to basis A, multiply both sides of this equation by A inverse. That would be A inverse. Okay. So let's do an example of concrete, with two concrete bases. So we'll do this example for R3. Okay, so suppose basis A, this is going to be a basis for R3. And here's another different basis for R3. So let's just first practice looking at coordinate vectors. So suppose you take a vector in R3, right? So this is a vector in R3, and it's the vector 1, negative 1, 1. What is the coordinate vector of this vector relative to basis A? How would we find it? Okay, so this coordinate vector consists of entries which are the numbers multiplying the basis elements of A to give you this vector, right? So this is a vector such that alpha 1 times the first basis element plus alpha 2 times the second basis element plus alpha 3 third basis element gives you the vector V. Well, of course, we get a matrix equation out of this. The vectors become columns in our matrix. Alpha 1, alpha 2, alpha 3. And here's the right-hand side. Okay, notice what we're getting, right? Remember that we define the matrix A to be the matrix whose columns are the basis elements. This is A times the coordinate vector V relative to basis A to give you the vector V. I know this is strange notation, but the subscript is all important. This indicates that this is the coordinate vector, not the vector itself. And so how would we solve this system? Well, we can row reduce, so we can, A is invertible. So you can just multiply both sides by the inverse. So I'll do that. And the inverse of A, so you can find the inverse yourself if you'd like. ideas. Okay. So the coordinate vector is the inverse of A times the vector itself. In the sense that that vector is, I'm not going to talk about coordinate vectors with respect to standard basis. So we get 2, -2, and so this is the coordinate vector for this vector relative to basis A. Well, what then would be the coordinate vector for our vector B relative to basis B? Well, we can do the same kind of setup where we know that the vector V can be expressed as a linear combination of the basis elements of B. And then solve the coefficients or the coordinates in that linear combination. But let's use a transition matrix, right? So we have a formula. Okay, we know that's transition. Here's matrix B. Let's just get that out of the way. Again, I'm just sticking the basis elements in B into a column, the columns of the matrix. And B inverse happens to be Oh, that's a -2 right there, my bad. Okay, now just check it really quickly, it's a -2. Okay, so we have the coordinate vector with respect to basis A. So we'd like to multiply it by the transition matrix that takes coordinate vector with respect to basis A and returns the coordinate vector with respect to basis B. And if we remember that the matrix A times this coordinate vector gives you matrix B times this one. The formula is easy to remember, right? We would multiply both sides by B inverse. So this is going to be our transition matrix. So let's find it. Your book might give you a different way of actually finding this, where you augment one matrix with the other and you start row reducing. But I'll mention that in a second. Here's matrix A. All right, so we get 4, 2, -1. All right, -3, -1. Adding those up, so 2. All right, so apparently this is the transition matrix. Let's check. Okay, so this transition matrix should multiply the coordinate vector with respect to basis A, and we found that, 2, -2, 1, and return coordinate vector with respect to basis b. So let's check. We have 8 minus 5, negative 6, negative 4, negative 5. Okay. I think we need a calculator for this. So we get 4 to, and that's right. So 3. Something not matching my notes for 1 second. All right. So then E inverse. There's a 4 to negative 1, negative 3, negative 1, 2, 1, negative 1. That's right. Okay, maybe that's right. But I want to check if this is right. How do I check whether this, in fact, is the coordinate vector for vector v with respect to basis b? How do I check? Well, this coordinate vector apparently consists of the scalars multiplying the basis elements. That should give you v. So let's check. Right? 3 times 1, 0, 1. Okay, so 3 times the first basis element would be minus 5 times the second basis element plus 1 times the third basis element. Oh, that sucked. Okay, I get negative 2. Yeah, this is not too good. So 7 and 1. So I did something wrong. It all seems to fit. Well, this is right. If anybody can catch me a mistake, if I made one at all, please say. Okay. You need to know. That's right.
Les,
Yeah.
I think over here when he did the transition matrix times VA, 3, negative 5, 1, I think it should be 3, 2, or 3, negative 2, 1, I believe.
3, negative 2, 1.
I think so.
I'll double check that. Yep. Okay. Maybe that'll work. Alright. Does it work? You get 1, negative 1, and 1. Yay, okay. Right, so the coordinates times the basis elements of basis B should give you the vector. Okay. Sorry about that. That wasted about 5 minutes. So yep, that's an example of finding a transition matrix. So I should, I guess, mention how you don't have to find the inverse, you can actually row reduce and implicitly find the inverse. So if I wanted to find the transition matrix from A to B, I said that that was equivalent to B inverse A. Okay. So I could have done the following. I could have taken matrix B, that's going to be the matrix you want to, the output coordinate vector, augmented with matrix A, and start row reducing until B becomes the identity, and invariably this becomes B inverse times A. And so that would be your transition matrix. So that's a way of finding the transition matrix for two different bases using row reduction. So that would be B, then augmented by A, and then row reduce. That's probably useful. All right, then. Well, how much time do we have? So let's do another example where I'm not giving you the bases, but I'm instead giving you the transition matrices that go from one basis to another. So suppose we have a vector space V, and we have three different bases for it. Let's call them A, B, and C. And I'm giving you the transition matrices from A to B. Yeah.
The whole problem we do, like on the inverse matrices, what were we checking?
Well, we were checking because we found a transition matrix, multiplied the coordinate vector for with respect to basis A. This was the coordinate vector, and then we got the coordinate vector with respect to basis B, and we were checking that it was correct because we know that the coordinates, right, multiplying the basis elements should have given me the original vector, 1, -1.
So we essentially multiplied it by, what we multiplied by? We did 3 and 2.
So I was checking
Alright,
this. We were taking, in terms of matrix multiplication, we were multiplying, doing this, and we should have gotten the vector V. So the basis elements times the coordinates relative to basis B should give you the original vector V, the actual vector. So then we had a transition matrix from the basis B to basis C. And let's say that's, what's the dimension of my vector space, by the way?
We don't know.
We do know, right? So this matrix takes a coordinate vector with respect to basis A, right? And returns the coordinates with respect to basis B. Since we have two coordinates, they must be multiplying two basis elements. So our basis has two elements, or the dimension of V must be 2. All right.
So the dimension of V is
It's 2. That's right. That was just an off-the-cuff kind of question. All right. And what do we want to do with this? find a transition matrix, let's say from A to C. Right? And maybe also find a transition matrix from C to A. Okay. Well, what would this ultimately do? Well, this transition matrix takes a coordinate vector with respect to basis A and returns the coordinate vector with respect to basis C. Right, that's its job. But let's think of this as a two-step thing where we start with coordinate vector with respect to basis A, multiply this by the coordinate vector, the transition matrix from A to B. What would this return? The coordinate vector with respect to basis B. Now take this result and multiply it by this transition matrix. So I'm just multiplying both sides by the same transition matrix. All right. What does this return? Well, what kind of coordinate vector? It returns a coordinate vector with respect to what basis? C, right? This takes coordinate vector with respect to basis B and returns a coordinate vector with respect to basis C. So you see that ultimately, if I compose these two transition matrices, multiply them, I get a transition from A to C eventually, right? And we can think of this as visually like a commutative graph here. So we have B expressed with respect to basis A, B, and C. Transition matrix A to B does this. Right. Coordinate vector with respect to basis A, coordinate vector with respect to basis B. Transition matrix from B to C does this. And what we're looking for is this, right? That's our job, to find the transition matrix from A to C. So what we do is we just take the long way around, so to speak. We first apply this transition matrix, take the result, and apply this transition matrix. So we're just taking the seated groups, from A to C. Now, getting sloppy. So you start with A, go to B, and then from B, go to C. So this says that you simply want to multiply these transition matrices. You just have to know the order. So you can either remind yourself kind of algebraically, how would you multiply these transition matrices, or maybe a graph. Okay, so there we go. This is going to be transition from B to C times transition from A to B. So there you go. 21, 28, and 10, negative 11, negative 14. That would be the transition matrix. Now, what about the other way? What if you want to go from C to A? Well, let's maybe do a simpler question before we try that one. What's the transition matrix from B to A? Well, we know that the transition from A to B will multiply coordinate vector with respect to basis A, return a coordinate vector with respect to basis B, and this matrix is invertible, so you can multiply both sides by the inverse of that matrix. Okay. So apparently, this matrix times the coordinate vector with respect to basis B will return the coordinate vector with respect to basis A. So this is the transition matrix from B to A. So that's the relationship. Yeah, the transition from B to A is the inverse of the transition from A to B. In our example, this is from A to B, so let's invert this thing. We get the determinant is 1, and we exchange the diagonal entries, change the sign of these out diagonals. And so what would the transition matrix from? So let's keep that in mind. And what is the transition matrix from C to B? Well, that would be the inverse of the transition matrix from B to C. So, inverse of this matrix. So negative 12 plus 10, that's a determinant of 2. So 1 over the determinant. Okay, there we go. So, right, graphically, all we're doing is like this goes from A to B, the inverse of this matrix will go the other way. B to A. So you think these are inverses of 1. So if you want to go from C to A, you would go this way. That will help us answer the question we had originally. What is the transition matrix from C to A? That was the question. Well, clearly it's going to be, there's so many ways to think about it, I can't even say that. There's a transition from C to B, and then transition from B to A. So just the product of the inverses, if you will. Of course, we could have just inverted the transition from A to C, but we could have done that. We already found this matrix at some point. If we found its inverse, that would give us exactly the transition from C to A. So negative 6, negative 20, 20, negative 10, and then negative 30. So this is feeling right. Maybe 5 and 16 is 20. Was that the inverse of the one we, does that look right?
Yeah.
Oh, that's, okay. So transition from C to A. All right. Any questions? Let's do something similar to number 3. It's a little tougher. Okay, so this is an interesting problem. It makes you kind of contend with some of the principles involved. So this is a basis for a vector space. It's a 3-dimensional vector space. This is a different basis of the same vector space. Well, actually, let me not say that yet. suppose I define V1 to be U1 plus U2. Define vector V2 to be U1 minus U3. And vector V3 to be U2 plus U3. Do these three vectors that we've just defined, do they form a basis? Okay. So does the set form a basis? Or a three-dimensional vector space? Well, first, okay, we can, well, to show that something's a basis, you want to show that it spans the space, right? And that it's a set of linearly independent vectors. So let's start with that. Like this is a set of linearly independent vectors. How do you check for linear independence? What's the equation you write down first? You create this combination, this linear combination of the vectors in question, set it equal to the zero vector, and then you solve for the coefficients. And then if the only solution you get is that those coefficients are zero, then you have linearly independent vectors. If you find a non-trivial solution for the coefficients, then we have linearly dependent vectors. So let's just do this. So, and what I would want to do is rewrite the v's in terms of the u's, because we know that this is a basis, as we said so. So then we can take advantage of the fact that this being a basis, we have linear independence with the u's, and so on. So let's do that. C1. That's V1. Okay, that's V2. And V3. Distribute the scalars and then combine. We have C1 plus C2 times the vector U1. And we have C1 plus C3, correct? Times U2. And then we have negative C2. That's right, negative C2 plus C3 times E3. All right, so how do we at this point take advantage of the fact that U1, U2, and U3 form a basis? Well, we have a combination of basis elements, U1 through U3, that's set equal to 0. So by the linear independence property of basis, these coefficients must be 0. So this gives us a system of equations. C1 plus C2, 0. C1 plus C3, 0. This is all by linear independence. The u's. And we can solve this system, right? So we can solve for the coefficients. So here's the corresponding matrix equation. Coefficients times the unknown c's equals, and so I guess we can augment derivatives. And what's the quick way to check whether we have just the trivial solution or we have infinitely many solutions including non-trivial ones? Well, we know that it's that whole, like if this matrix is invertible, then we have a unique solution, and this matrix is invertible if the determinant is not 0. So if you quickly find the determinant of this matrix to get our answer, I'll just go ahead and write this. All right, let's row these. Clearly, the determinant of our matrix would be 0 because we have a row of zeros here. So we know that's that these do not constitute a basis. So we have, for example, C3 could be equal to -1, then C2 would be 1, and C1 would be 1. Okay, so the claim is that we found a non-trivial solution. And it's true, right? So you have, right, so C1 times D plus C2 times D2 plus C3, so -1 times D3. You said that that you think that should be 0, and it is, because V1, V2. I'm just checking that it's right. Minus. So we get, oops, ice, whoa. This should be -1, shouldn't it? So, right, now I was reading that incorrectly. This last row says, the first row says C1 plus C3 is 0, so if we let C3.
What's the uncorrected?
What am I doing wrong?
Why do we know the value of C3?
We don't, we just chose it because we have infinitely many solutions, right? And all we're after is a single solution for these coefficients where at least one of the coefficients is not 0. And you already found it, I just wanted to demonstrate it. And I think I'm messing up because this should be -1. Okay, the second row reads, C2 minus C3 is 0. If we just simply let C3 be -1. That's non-zero, right? So that's plus 1. So we see that C2 would have to be -1. I made that mistake. So there we go. And now it works because you have U1 minus U1 is 0, U2 minus U2 is 0, U3 minus U3 is 0. But the point is that there's a non-trivial linear combination of V1 through V3 to give you the 0 vector. This set is not linearly independent, it's linearly dependent. Therefore, this set cannot be a basis. All right, that's not a basis. Okay. Now, if on the other hand we did something like, so I'm going to start all over here, and I'm going to create something that is a basis, so this works. Okay, that's going to be a basis. You would verify that this set of 3 vectors is going to be linearly independent. We can do that really quickly. Right, if I, so my, this will be C1 plus C2 is 0, C1. Now, if you look right at this equation, I won't go through it, but we can quickly find the determinant of this matrix. The determinant of our matrix is not 0. I believe it's going to be -2. Okay. So it's not 0. Therefore, we know that the only solution for these coefficients is that they all must be 0. Therefore, we have linear independence. And we can just maybe cite a theorem in your book that says that if you have 3 vectors in a 3-dimensional space, where the vectors are linearly independent, they automatically span the space, right? So we have a basis. This is a basis. Or a 3-dimensional vector space. And now we just need to maybe find transition matrix from A to B. Something like that, B to A. So the next problem might be find the transition matrix from A to B. Yeah, so this is, we can't use our little recipe, like we can't say that this is B inverse times A. Why? Because we don't have the actual basis vectors, right? We just have letters. So, the way we could do this is, oh crap, that would take too long. Okay, it's time. So I won't complete this problem, but if you need help with it, you can always come to the math lab. And don't forget to sign in